this video, we are going to learn how to construct the binary order rooted tree from the three expressions, that is infix, prefix and the postfix. This is very important topic in a graph theory, especially in expression evaluation and tree traversal. Before we start, let's quickly understand what the meaning of binary order rooted tree. Binary order rooted tree has exactly two children for every internal vertex, and tree has only single root. Moreover, whenever we are working with the expression tree, operators are always as a internal nodes and the operands are leaves, or we call it as a terminal nodes. What do you mean by operand? Operand means it is a variables or constant. So if we have constants in an expression, so they always act as a leaves, whereas the operator like plus, minus, multiplication, divide, they always treated as the internal vertices. Now let's start with the first case, infix expression. In this case, we need to construct the tree from this example. Now before moving to the construction, let's understand what does it mean. If we study A plus B, as per the infix, it is a in order. In order means left, then root, then right. So it means this is the left of plus and B is the right of plus, where plus acts as a root. Now if we study the next operator, that is a multiplication, in this case the left side is the left subtree, or we can call it as a left child of multiplication, and the right side is the right subtree till this, because the bracket is till this. Next operator we have in subtraction, and this subtraction means its left side is a C and the right child is the D. Now move to the next expression. Next expression is between this bracket and this. It means this is the left of this divide and the right of the divide is this. And for the subtraction, it is between this bracket. So left is a 4, right is a 8. Now we need to identify what is the main root in this expression. So main root is always given without bracket. So plus is a part of this bracket, multiplication is a part of this entire bracket. This divide is not the part of any of the bracket. So we call it as the main root of the tree. On its left subtree, we will take this expression. In this expression, identify next root of the subtree. So this is the root of A and B, not for this one. Subtraction is the root of C and D. It means multiplication is the root of both these and both these. In short, for this bracket, the next root is multiplication. Now, do we have its left child? Yes, because on the multiplication, the left side we have this expression A plus B. In this expression, again find the operator, that is the plus. It means plus is the next root of the next subtree. On its left side of the plus, do we have any operator? No. It means there does not exist any subtree after this one, but it has a left child, that is the A. And the right child is B. Right now we have done with this. So this is the left of the multiplication. Now we have the right of the multiplication. On the right side, we have the expression C minus D. Again, we get a root from here as the subtraction. And its left side is C, right side is D. It means we have done with these vertices. We have constructed the ordered rooted tree for this. So divide left portion is completed, on the right portion, we are getting another root as the subtraction. Because root, or we can say the internal vertices, are always as an operator. On the left side of the subtraction, we write 4. On right side, it is a. So this is the final order rooted tree of the given expression infix. Next we have constructing tree from the prefix expression. Consider this example. We need to find the order rooted tree from this prefix expression. Now before moving to the order rooted tree, so we have two important rules. That is, in any of the expression tree, remember that operators are internal vertices and constants or variables are the leaves. So in prefix notation, we always read root first, then left subtree, then right subtree. We do not immediately start from the main root in this case. We are starting building the smallest subtrees based on the prefix pattern. Now let's look how such pattern exists in this case. First we will look for the operators, variable, variable, or we need operator, constant, variable, or we can swap these two one, or we have the constant. So if we have this form, first we are going to make the subtree of such form. Like in this case, this is the operator, next is also operator, next is operator, next is variable, its next is again variable. It means first we can make the subtree of this one. Let's read the next one. Next is operator, its next is variable, next is variable. Again we are getting this form. Next is subtraction, next is constant, next is variable. So again we are getting the same form. At the same time we can make the subtrees for these three things. So for the first case, in this case, root means plus, left is A, right is B. As per this one, root is subtraction, left is C and the right is D. For the next one, subtraction, left is 4, right is A. So we have covered these things. Now we have the expression as divide plus one expression, second expression as a variable, and the third is also a variable form because it contains variables. Now again we can look for this form, operator, variable. That is here. So in this case, plus is root, left is first variable and the right is second variable. After doing this one, what type of form we have? That is divide, new variable form, let it be a V3 and it is a V4 as it is. So again we can write its order rooted tree. Root is divide, left is V3 and the right is V4. Now just plug in the values over V3, V4 here. For V3 is this because in place of this one we have mentioned V3. So we can write here as a plus, left is V1, right is V2. V4 is this expression, write the expression of V4 here, minus left is 4, right is A. Now what is the value of V1? V1 is this. So write the value of V1, that is plus, left is A, right is B. V2 is the value of this, that is minus C and D as the right. So this is the final order rooted tree for this prefix expression. So for prefix, remember it is a pre-order, that is a root left, right. And root is always operator. Left and right, we can treat it as the leaves, and that is always either a variable or a constant, but can never be a operator. Based on the same procedure, let's find the rooted tree from the postfix expression. We need to construct the order rooted tree from this postfix expression based on the previous procedure. So in the previous procedure, we are working with the prefix. Now it is a postfix. Postfix means first we need to visit at the left side, then right child, and then root. And root is always operator, whereas for the left and right, we are just looking for the variables or constants together. Either they are both are variables or both are constant, maybe one of them is constant. But make sure the root is always operator. So in this case, variable, operator. It means we can draw the order rooted tree first for this. C, D both are variable and the next is operator. At the same time, we can draw the order rooted tree for this. Next is operator, but we are not going to operate first this one. Its next is constant variable operator. So apply the same procedure in this case as well. Suppose whatever the order rooted tree we have, take it as a variable v1, v2, v3, and this plus and divide as it is. Now again we are getting a variable operator. Suppose it is a v4 and v3 as it is, divide as it is. Again we are getting variable operator. So that is the final form. So let's break it one by one. In this case, we can start from the last one. So first is divide. Left is V4 because left, right, then root. So this is the left and this is the right and the root here. V4 is the value of this one. That means first we have the left of this one, that is V1, right is V2 and the root is plus. For V3, we need to draw the order rooted tree of this one. So this is the left, right and this is the root. Root in this case is subtraction. Left is 4, right is 8. For V1, that is AB plus. Root is plus, left is A and right is B. For V2, C is a left, D is a right and the root is subtraction. And this is the final order rooted tree from this postfix expression. So we need to remember for the postfix, first we need to travel as the left, then right, then root, and root is always operator. And for the left and right, we are looking for the variables or a constant. And now we have constructed the order rooted tree from the postfix expression and the prefix expression. Now we will learn how to evaluate the postfix expression and the prefix expression without constructing the order rooted tree. The concept is same. For example, in this case, we need to find the expression value without order rooted tree. So how to do that? First, we will identify whether this is a prefix or a postfix. Postfix means first we traverse the tree in a post order, that is left, right, and then root. And recently we have covered that root is always operator and we take left and right either variable or a constant. Right now we are dealing with the constant only. So we need just constant and operator form. If we have this form, we will evaluate that in a post order. Whereas if it is a prefix, it means we are traveling the tree in a pre-order, means first root, then left, then right. And root is always operator, whereas left and right is always constant in this case. So if we have operator constant form, then we will evaluate that. Now whether this is a prefix or a postfix, as the operator is at the end and operator is end only in the postfix, so it means it is a postfix expression. Whereas in the next case, first it starts from the operator and operator is always root, so it is the prefix notation. Now how to evaluate the postfix? Look for the same concept, constant operator. Like in this case, constant and next is operator. It means first we can evaluate this. Now how to evaluate this? Left is a 6, right is 2 and plus is root. So we treat it as 6 plus 2. That is equal to 8. Do we have the same format in this expression? Let's look into that. Next is operator. Then this is a one single constant 12 because it is represented together, not as separately. Again constant, and the next is operator. So we have constant operator form here. So it is a left, then right, then root. So we write 12 divided by 4. Answer is 3. Now remaining portions of the expression is 5. It is a multiplication. Here subtraction. Repeat the same procedure. Do we have a constant operator form? If we have that, we will operate that. That is 5, 8 multiplication. So 5 into 8. That is 40. 3 as it is, subtraction as it is. Now again operate this. We have 40 minus 3, that is the 37. So final answer in this case is a 37. Repeat the same procedure for the prefix, but the form is different. That is first operator, then constant, then constant. So it is operator, but the next is not constant. Here it is operator, but the next is constant, but its next is not constant. Let's take the next case. Operator, constant, constant. It means first we are going to treat this one. And how to write this? This is 6 plus 2. And the final answer is 8. So this subtraction, this multiplication and 5 is as it is. Do we have the same format in the same expression? Yes. That is the operator, constant, constant. So together operate this, we have 12 divided by 4. That is equal to 3. Now find the same form in this expression, operator, but the next is not constant. Here we have the operator, next is constant, again constant. So we can operate this as 5 into 8. And the answer in place of this is 40. This subtraction as it is, 3 as it is. Now 40 minus 3, that is equal to 37. So this is how we are evaluating the postfix expression and the prefix expression without evaluating order rooted tree.